So in this problem, we kind of have to think about acid-base chemistry from the perspective of whatever is the strongest base. And so you want to think of which one of these is the most unstable. So if we look at all of them, what they have in common is if you imagine they all had hydrogen on it. So this would be methane CH4, ammonia CH3, water H2O, and hydrofluoric acid HF. So once you remove the hydrogen on there, these are basically what would behave like a conjugate base. So if we take it from that perspective, which one of these would be the least stable? So carbon, nitrogen, oxygen, fluorine, which one of these with a negative charge does not like to have the negative charge? And if we go by what's on the periodic table, that we will see, if you remember, that carbon is the least electronegative. So going across the periodic table will not want to be carbon minus, and so A is going to be the most basic of all of these. Okay, so in class we've talked about nomenclature. There's some videos that you can practice with it. So this is a quick practice to help kind of go over some of the things that we need to do when we name something. So first we find the longest chain, and if we were to start here and follow along and go in this direction, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. Now, if we were to try to go in a different direction, and any one of these methods will work, 1, 2, 3, 4, 5, 6, 7, 8. So we have 1, 2, 3, 4, 5, 6, 7, 8 in this direction. Here we have 1, 2, 3, 4, 5, 6, 7. So going from left to right is actually not going to give us the longest chain. And so that is one thing to look out for. A lot of times we want to read from left to right or right to left. And sometimes we have to go zigzag up and down, diagonal in different directions. So it turns out we do have to go kind of in this direction, and we have 8 carbons. 8 carbons is octane, so we know that the parent chain is octane. And we also see we're going to want to name at the side that has the most substituents first. So if we look along the chain, we'll see, we really don't start any substituents for a while going on this direction. So we do see that we have methyl, methyl, we have another methyl, and then we have this isobutyl group right here. So we could potentially go in this direction first. So we're going to, so first we look for the longest chain, so we did that. We can number the carbons, so I can go 1, 2, 3, 4, 5, 6, 7, 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Actually, that was 9 carbons, sorry, so that's nonane. And so if we number the carbons that can help, we're going to go from the side that has the most locants first. So it's going to start in this side. If we had gone in this direction over here, you wouldn't actually get any locants for very much. So our locants really start earlier on the top part. We have 1 methyl, 2 methyl, 3 methyl. So we would use trimethyl in the name. There's 2 methyls in the same position, so when we number it, it has to be 2, 2. This one had to be 4, so it would be 2, 2 trimethyl. Over here, the isobutyl would be in the 5th position, but remember, we don't count iso when we do the nomenclature, so butyl comes before methyl, so it would be 5 isobutyl. 2, 2 trimethyl, okay? And then we also want to make sure that we have numbers that are separated with commas between numbers, and between numbers and letters are dashes. So that's kind of like something to think about. So that's a quick practice for you to practice doing that. All right, so in this video we talk about Newman projections, and so that's what most of the video is about. So understanding Newman projections has a lot to do with understanding strain. Strain actually determines a lot of things that happen in processes and reactions and so on. And there are different kinds of strains. So the most common types of strains that we will see is steric strain. Steric strain just means that you have electrons that are very close to each other and they repel each other and they don't want to be near each other. Torsional strain is related to steric strain. It's just a type of steric strain, but it's associated with things when we're talking about the movement of what we call staggered and eclipse conformations, which will come up in this video. So that it's very specific. So torsional strain has to do with rotation, so rotating something, and that's what, when we talk about staggered and eclipse, we're talking about rotating conformers. And angle strain, kind of as it seems, it's related to angles. So when we're talking about rings, that's where this is going to be most relevant. So here is a question before we get started a little bit more, and it's a nomenclature question. I'm going to help you a little bit. So we do want to name our substituents. We see a hint here is that some are octane and some are nonane. So think about your longest chain if I went straight this way versus this direction. Going in this direction, I'll have more carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, 10. So going in that direction is 10. Going from left to right or right to left straight, that's only going to give us 9. So that helps us to eliminate some of our answers. So it's going to be decane. And then we want to number giving everything the lowest locants first. So we can kind of get a sense just looking at the answers, some ideas. So chloro alphabetically should come first, so that eliminates these two. And I'm going to remind you, we want to give things the lowest locants possible. So I gave you some big hints right here. All right, so soon test number 1 is going to be coming up, and we're going to be talking a little bit about chair conformers. Today's, the beginning mostly talks about a lot about rotating around conformers such as eclipse and staggered. So I'll expect that you know general nomenclature and things related to chairs, like you know, the term ring flip, although I'm not going to have you do it on this test, equatorial and axial. But when it comes to the di-equatorial, the di or multiple substituents on a structure, I'll put that on test 2. But for this one, understand, you know, equatorial is more stable, that kind of thing. The last part of test number 1 is going to be the last thing that we'll cover, and that's just the basic understanding about what mass spec, spectroscopy, IR, spectroscopy and NMR spectroscopy is. So just to give you just as a preview, mass spectroscopy basically helps us determine the mass of a compound, so how much that compound weighs, and you'll get these fragments that help us determine what did the structure kind of look like. IR spectroscopy purely helps us figure out functional groups for our class. There's more that it can do, but that's mostly what it's going to do. And NMR will help you to figure out structural features. So for instance, you may have 2 isomers. How do we distinguish the 2 isomers? NMR can help us. Mass spec won't help us. IR won't help us generally, because they're going to have, conformational isomers have the same mass. Maybe some of the fragments that we may pick up, which we'll talk about more of, you can determine. But if they have the same functional groups, IR is not going to tell you anything. So NMR is the big one. It will help us determine our structures. And so for the rest of the video, we'll go more into stuff from chapter 4. But again, I just want to point out that the very end about having multiple substituents on the ring, I will be putting that on test 2. Even though we'll cover it a little bit, we're going to talk a little bit more about it after the test. And then we'll finish up spectroscopy after the test. So for this, you're going to know the basics, but you're not going to have to interpret spectra to a great depth.
This model of black are the carbon atoms, the gray are the sigma bonds, the white pieces are hydrogens, and the blue pieces are 2 other elements that I'm going to represent as being the same thing, but I want to distinguish them when we're looking at the Newman projection, so I'm just going to use 2 different colors. So we can say they're 2 methyl groups. And this is just for the purpose of distinguishing these things. So Newman projection is just a way of representing your structure in which we're looking at one carbon and looking down at the other carbon, so we're kind of blocking it out. So if you can see this, it's a little, maybe a little hard to see, but you'll see that I have one carbon blocking the other. The two hydrogens on the left-hand side are kind of on top of each other, and the white, the hydrogen, and the red atom are blocking each other. The blue atom is blocking the white atom in the back. So you can sort of see it, and I can turn it slightly to an angle. That's called sawhorse when they're at an angle, when they're right on top of each other, their Newman projection. And so I can rotate this. So this is what we call staggered, when we have all the atoms that are alternating from each other, and they're not on top of each other like before. So you can see in the sawhorse form, they have a dihedral angle of about 60 degrees from each other. So if I rotate every 60 degrees, you'll see we'll go from staggered and then we'll go to eclipse. I'm going to pause for a second and go to eclipse. So eclipse is when they're on top of each other. Now if these were all hydrogens, the eclipse is the worst that you can get, and when they're staggered, that's the best you can get. And so that's when you have these torsions. And so you get your angle strain. Now I'm going to rotate again. So let's just pretend that the blue and the red are methyls. I'm just using them to differentiate the two methyl groups, and they're eclipsed from each other, but they're close. And one thing about our models that are a little hard to see is that when they're like this, they look smaller than they are, but remember the methyl is a lot larger than the hydrogens. So you can imagine these large groups, and they're close to each other. They're not touching each other, but they're close to each other. So this is not favorable. Now when those two groups are eclipsing each other, that's even worse. Remember, again, these are two large groups. I know your models don't look that way, but imagine that they're a lot larger. They're enormously larger than the hydrogens, and they're on top of each other. So if we look at kind of the sawhorse form of it, right, you can imagine these two large groups next to each other. They're going to have a lot of electron repulsion, and that electron repulsion puts them in a position that's not very stable. So when they're eclipsing like this, okay, they're at the highest energy. I'm going to rotate this around. Now they're completely opposite to each other, and we call that anti. So they're staggered, but they're anti. When they're anti to each other, meaning opposite, anti means opposite. So when I'm anti something, I'm against that something, I'm opposite to that something. This is the most stable you can get. You get your two largest groups away from each other, and it's the most stable that you can get. Another way that they can be further away, we've seen this before. It's not the best because they're close to each other, they're not opposite to each other, but this is called gauche. Gauche is when they have like a 60-degree angle from the two largest groups. That's not as stable, but it's more stable than the eclipsed.
Looking at the models, we can now draw what these Newman projections look like. And so the way that we represent them is that you have the first carbon that you're looking down at. And so let's say that's this front carbon. And then you have each of the elements on there. And then what's behind the big red dot that I put on the screen, the dot in the middle, behind is the other carbon. And so you would imagine that the other groups, I'm going to call them A, B, and C, are behind. So the way that we translate that is that we make a big circle. And then what's on the front of the circle are what's
in the beginning, in the front. So this is our carbon right here. Again, I'm going to call this XYZ. I'm not in any particular order. The carbon that's in the back, we can't see. So that's blocked. And so we can pretend that what you see with your hand around the model blocking the back is that circle. So I can imagine if I were to put my hand around my model, so let's pretend this is my model, and let's pretend you put your hand, these are your fingers, around blocking, and I know I'm not an artist, and this doesn't really look like a hand, but you get the point. You block the back. This is what you're seeing. And so what would be poking out from the back are the other atoms. Okay? Using the model that I had made, this is what you saw. These were the black carbons. You had the white hang down. This is an eye. These are eyelashes. You're looking down one carbon at the next. This form is our staggered form. And let's pretend this is the red one, and this was the blue one in the back. So if we have the red, and let's pretend this is a blue, when they're next to each other, we call that gauche. When they're opposite to each other, that's anti. And we're going to draw these at a slight angle, only because it's going to be hard for you to see when they're on top of each other otherwise. That is when they're eclipsed and they're really bad, okay? So you can eclipse and they're on top of each other in multiple ways, but this is the worst one. So that's Newman projection, and so we'll practice that in class. What is actually happening here? So when we had the black carbon atoms with the blue and the red pieces attached, use that to represent some methyl groups. When they're on top of each other, that's going to cause us overlap, and that overlap is what eclipsing is what we're going to call sterics. And sterics is just a way of saying that your electron orbitals are actually too close to each other, and that's a problem. Now, with having your molecule in the eclipsed form, you're going to have your two bonding molecular orbitals overlapping on top of each other. So remember, each of these bonds represents electrons coming together to form bonds. So you get these bonding molecular orbitals. When they're on top of each other, that's not good. Now, your antibonding orbitals are at a different angle. There's no electrons in them. So them overlapping is not a big problem, and actually them overlapping can actually be a little bit more stabilizing because you can share the electron cloud through it. So when you're eclipsed, you actually have a problem with the electron clouds being on top of each other. When you're staggered, you actually have the electron clouds from the carbon to whatever bond that element that you're bonded with. Actually, they can overlap with the antibonding orbitals, which is actually not a bad thing. That's favorable because you're overlapping with something that doesn't have electrons in it, which is what you want. So torsional strain happens as a consequence of rotating. So when I go from something that's stable to something that's not stable, there's an energy associated with that. It costs me energy to rotate to the eclipse form from the staggered form. So, like I said, there are different kinds of strain. Steric strain is just a generic word for when you have electrons repelling each other, when they're too close to each other. So when the carbon to hydrogen bond in the front and the back are on top of each other, that's steric strain. When you rotate, the act of rotation causes torsional strain because you rotate that energy to get it into the eclipse form is actually unfavorable. And we'll talk about angle strain separately. That has to. Alright, now that we've looked at Newman projections in general, let's look at the consequence of the Newman projection and the torsional strain that's happening on the molecule. But for simplicity, let's look at ethane first. We will look at more substituted molecules and draw examples in class. But on our ethane, when we have these hydrogen-carbon groups, when they're close to each other like we see in the eclipsed form, you're going to have a molecule that now has so much energy associated with the electron density being very close to each other, the electron clouds being so close to each other, that is going to want to force that thing to turn. So it's like magnets that are just forcing and flipping the molecule away from the orientation because of the repulsion that's going to happen. So that torsional strain that's associated is a repulsion, and there is an energy that's associated with that potential energy. It's the force wanting or making the molecule have the potential to spin in a more favorable form. And so when everything is in the staggered form, that's the most simple way to have all the electron clouds furthest away from each other. When you have a dihedral angle of about 60 degrees for each group and they're not on top of each other, then we actually have less interaction. But as we rotate, you go from eclipse to staggered, and all of the staggered is going to be the same energy because they look the same, right? All the eclipse have the same energy because they look the same. Now, if we were to replace the carbons with other groups, the size of the group will matter. The in terms of size, meaning the size of the atom, or the number of atoms present. So if we're talking about methyls, for instance, those are pretty large in comparison to hydrogens. You want those things to be further away. So the antiposition is going to be more stable in the staggered form because there is less repulsion of those groups in those positions. So far we looked at Newman projections, the antiposition in the staggered form and the eclipse form are actually the best. And so putting your largest groups in the antiposition, meaning opposite to each other, is always a good thing. Looking at this with building models is one of the best strategies that you can use, and so that's why we require that you have model kits, and we're going to need that in class. Our next thing is to look at rings, and so we're going to look at some terms called axial and equatorial. You read about that in your book, and looking at putting your where your groups go to be more stable. So in nature we see rings a lot, and actually some rings are better than others, and that's because of the bond angles that are going to have to form. So when you have a butane structure where you have 4 carbons in a ring, your structure is going to want to adopt a 90-degree angle. But remember, sp3 carbons are 109.5, so that's highly unfavorable. When you go to a 6-membered ring, we know that 6-membered rings are the most stable from what you read, but they're the most stable not because they form these hexagons, because that's not actually very stable. What they actually form is what's called a chair. 6-membered ring is actually the most stable, and it's the most stable because it forms a chair. 5-membered rings are a little bit stable, not as stable as 6. 7-membered rings are stable, but not as favorable as 6. And it's just because of the adoption of the chair. The chair allows us to form the 109.5 degree angle for every carbon. And what is the chair? Well, the chair conformation is drawn in a way that puts one tip of the ring pointing up and one tip of the ring pointing down. And I'll display that to you guys in the models. So this is the conformation of a chair structure. You can see some of the elements are pointing straight down, some are pointing straight up, and some of them are pointing across. So these are across, we call these equatorial, the ones that are kind of at an angle. The ones that are up and down are called axial. So you know the Earth spins on its axis, which is north and south. Equatorial is east and west, so this is equatorial. And you can see that there's 3 down, 3 up in the axial. There's also 3 down, 1, 2, and then the other one here, down for the equatorial, and 3 up for the equatorial. And so this is a chair structure, and if you look very carefully, you'll see this carbon is basically pointing down from this one. This is more up. So if you were to look at it carefully, this is up, that's down, this is up, this is down right here, and this one is across is up. And so the chair conformation, we can see that I put this red and blue atoms. We'll pretend those are methyl groups, and right now the red one is axial up and the other one, the blue one, is equatorial up. And so that means they're in the same direction. When they're same direction, we call that trans. Now I'm going to do what's called a ring flip. So now that I've done the ring flip, you'll see that what I did was where the atom that's red, it was up axial, now it's equatorial up, and the blue one is axial up. And so all I did was rotate them, and we'll do this in class, so that they're now in different directions. Now they're still pointing both up, so that's cis. And so we'll see that with our structures, where you see the ones that are axial, though it's a little hard to tell because the atoms are not quite the right size. If you imagine that this is a methyl group, it's huge. We have what's called a 1,3 diaxial interaction, where if this is 1, this is 3, and this is 3 on the other side. 1,3 diaxial interactions are not good. So axials are typically not good. So if you can put larger groups in the equatorial, that's the best thing that you can do for these types of structures. And so we'll do some ring flips in class. So you're going to need to have your models in class. Here are some questions to wrap up our video. So from your reading, which of these 8 carbon structures would be most stable? So a hint is the more substituted a molecule is, the lower in energy it's going to be in terms of heat of combustion. So the more substituted it's going to be, the more stable that molecule is going to be. The less substituted, the more unstable. So I'll give you a moment to think about the answer to this question. Now we learned about rings. Which of these rings is the most stable? And the review question from the previous chapter is about acid-base chemistry. So look at this molecule. This is more of a question that has multiple things associated with it. Look at this molecule and decide what is the most acidic, what's the least acidic, and try to fill in the middle.